the slides. So let's start with like a quick pop quiz. We were trying to do this last time, but there was not enough time. And I'm assuming you can see my slides.
Yes.
Okay, great. So remember, like last time we were looking into how we can make a CNN architecture fully convolutional so that we don't have to use any fully connected layer. So this was like the architecture for our CNN. We started with like 14 cross 14. Just give me a minute. Okay, I think now it's better. All right, so we started with 14 cross 14 cross 3, and this could be like your input image or any kind of data with spatial resolution of 14 cross 14 and 3 channels if it, let's say it's an RGB image. And so this arrow here, it's showing your network's layer. In this case, it's a convolution layer, and the kernel size is 5 cross 5 cross 3. All right. So whenever we are showing like these cuboid shapes, these are your feature maps. And whenever we are showing like these arrows represent your network layers. Okay. So in this case, it's a convolution layer using this kernel of shape 5 cross 5, and this is a max pooling layer of shape 2 cross 2. Okay, and this dimension here is the shape of your feature vector, which you will get after applying this layer on this particular input. Now, in a traditional neural network, what you will have is you will have your input, your convolution layer, then you have a max pooling layer, and you just use like a fully connected layer on these feature sets. And of course, what you'll have to do is you will have to flatten your features before passing it to a fully connected layer. So in this case, it will be like 5 cross 5 cross 16 neurons pass to this fully connected layer. And then again, you have fully connected. And this also is a fully connected layer, which is predicting 4 neurons. And the same network for fully convolutional network, but the only difference is instead of a fully connected layer, you have a convolution layer, all right, which gives you a 1 cross 1 cross 400 different channels. And again, you can apply like a 1 cross 1 kernel on this feature map. You will get something like this. Okay, so you are getting 400 because you are applying 400 such kernels. Okay, so each neuron will be produced by one kernel, and this kernel will be of shape 1 cross 1 cross 400. Okay, 400 is the depth number of channels you have, and you can predict like again 4 neurons, which is exactly the same. Now the question is, which of these two parameters? So you can take like 1 minute for this.
You cut out there on my end. What?
So the question is, which one of these two networks will require fewer parameters, less number of parameters?
Oh, hi, Professor. I have one question. That what is the 5 by 5 before the first fully connected layers means? It's pooling?
You mean like at this point?
Yeah, the lower part below it
This
is
one?
there is a 5 by 5. Yes. No.
5.
The fully convolution layers. Yeah.
Okay, this is a 5 cross 5 convolution kernel.
Oh, okay.
Which will have like a shape 5 cross 5 cross 16 because of these 16 channels.
Okay, thank you.
Okay. Okay, so I think most of you got the right answer. Some of you are saying A and C, and so B will be the right answer because this convolutional network will have fewer parameters. And the reason is, so until this point, both will have same number of parameters, right? It's the same architecture. Now, from this point onwards, we discussed last time that these layers are almost identical. Okay, I will cover that again today, but let's look at this particular layer where it's like the main difference. So when you're applying a fully connected layer on these many features, so this is like a 400 neurons, right? And you're connecting 400 neurons to again 400 neurons. So that means you require like 400 times 400 number of weights, right? To generate each neuron, you will have to take a linear combination of all the input neurons. So taking that linear combination will require like one weight for each neuron. So that's like 400 weights for one neuron. And you have 400 different neurons. So it's 400 times 400. All right. Now, in this particular case, you only have this convolution kernel, which is shared across all the spatial regions, right? So one convolution kernel will have 5 cross 5 cross 16. Okay, so that means it's 25 and 16. Okay, that's interesting. So I didn't realize that. So this kernel will have 5 cross 5, 25, and then 16 depth. So that's around like 400. Okay, so this kernel is 400, and you're using the same kernel at all the positions. Okay, and then you are so applying at one location, it will give you one neuron, right? And you can only apply like once because the spatial resolution of this feature map is 5 cross 5. So you'll have to put it like at the center, you get one value. And to get the second neuron, then you need a second kernel, again, which will have a shape of 5 cross 5 cross 16. So it means that to get this to this layer, you need like 400 times 400, which is kind of equivalent to this. And I didn't realize that, I didn't do the math earlier. So it means that both of these networks will have similar number of parameters. Okay, so any question on this layer? Then we'll talk about the following layers.
But there will be less biases, right? Because the one bias per each filter, as the first one has one per each neuron.
Yeah, let's just ignore the biases because I mean there are different ways you can use biases, right? So in this case, you can have one bias for each neuron. Similarly, you can have each bias for each neuron in this case as well. So that's like, I mean, if you want to have different biases for different neurons, you can do the same for this layer as well. Okay, so okay, wouldn't the later layers and B will be different? So I'm coming to the later layers. So any question before we move forward? So we just see that these two layers are almost identical. Okay, now if you look at this particular layer, your kernel shape is 1 cross 1 cross 400, right? Because of this depth. So to generate one neuron in this following layer, you need 400 different weights, and you need to generate 400 different neurons. So then you need like 400 times 400 different parameters, which is exactly same as this particular layer, where you are connecting 400 neurons with 400 neurons. And same is the case for this. You're moving from 400 to 4, and here also you're moving from 400 to 4. So that's why like these layers are also identical. So this is just a coincidence that this is matching. Okay, so I think There are a couple of questions. Can you please explain again why B is not correct? So we just discussed that. I will come to that again. Wouldn't the later layers in B be different? So Jacques, so now it's clear, right? Why these layers are also identical?
Yeah.
Okay, great. So Furkan, this was my one of the very few true answers that found out to be wrong. Okay, that's fine. Thomas is saying it's there 25 parameters for, isn't there 25 parameters for each of the 400 neurons for the conv? 25 parameters for each of the 400 neurons for the conv. So it's not 25, right? 25 is like just the spatial dimension, but you remember like we have to cover like the whole depth. So when you're doing 2D convolution, your actual shape of the kernel is a three-dimensional shape, right? It's X cross Y, and then you'll have to implicitly include the depth. So in this case, the depth is 16. So Thomas, does that answer your question?
So is it a three-dimensional kernel then that we're using here to convert it to the 1x1 kernels?
No, that's not specific to this particular case. This is like in all of your 2D CNNs, whenever you are performing a 2D convolution, it's actually 3D convolution, because the depth is implicit, right? So if you're using a 3x3 kernel, then the third dimension is defaulted to like whatever number of channels you have in your input data.
Okay, so the kernel size is 5 × 5 × 16, and then we've got
Right.
400 of those kernels.
Exactly.
Okay, all right, that makes
Okay.
sense.
So Shakib is asking, how could we make B with fewer parameters? So this we can actually make maybe the programming assignment. All right. So how would you set it up, the full con network to have? So again, the same question. All right, so we can skip that one. We can include that one in your programming assignment. So let's,
Professor,
yes.
I had a doubt. So, so this 5x5 kernel, 5x5x16 kernel, is then repeated over the image for like 400 times. Is that how it will work?
No, so in this case, your input shape is 5x5, right? And so we are not using any padding. So when you will place this kernel on this feature map, there is only one possibility for that, just the center. And I mean, you will use this kernel only once.
No, but how do we get the 400 in the?
So you will have 400 such kernels. So for each neuron, you will have one kernel. So it's like you have 400 different kernels.
Okay, but then that will increase the parameter, right? So that will be like 5x5x400.
No, it's not 5x5x400. It's 5x5x16. That's the shape of one kernel, and then times 400, because you have 400 such neurons, and that's why it's exactly same as this layer.
Oh, okay.
Okay. So the other question, like when you were asking how you can have fewer parameters, so think about why, like in general, a CNN has a fewer parameter when you compare that to fully connected layer. The trick is like you can share the kernels across like different spatial positions, right? And right now we are not sharing anything. We are just using the kernel ones. So if you use the same kernel for different locations, then actually you are sharing that kernel, and that will make it like more efficient than a fully connected layer. So think in that direction. All right. So let's move on. It's already 5. Okay. So nonlinearity and activation function, that's fine. We have already covered. You need activation functions to learn like complex functions. You need activation function to make like your predictions in certain ranges, right? So depending upon like whether you're doing synthesis or you're doing classification. Now let's quickly look at like different kind of classification. So another question was like, what's the difference between classification, recognition, localization, and detection? So let me clarify that. Classification and recognition, they are the same thing. They are used like interchangeably. And they mean like you just have to say whether a particular object category or any class is present in an image or your video, yes or no. All right. And localization means, and again, localization has different categories. So if it's spatial localization, then it means that in an image, you are telling where exactly that object is located. Okay. So that's called object localization. And it's also used in some other terms, like it could be temporal localization. For example, if you have a video and you want to detect the activity and also localize where it's happening. So if you say temporal activity localization, it means that in a long video, you are trying to predict on which frames the activity is happening. It could be like the starting frame, the end frame, okay, that span of the activity. And that also might not include spatial localization. So if you need both spatial as well as temporal, that's called spatial temporal localization. So you detect the temporal span as well as the exact location in the spatial extent as well. And that we also call detection. So if we are using activity detection or object detection, it means that you exactly know which object category you have and where exactly it's located in the image or in the video. Okay, so now let's talk about like different variations we can have in classification. We can have just binary classification, which means that you have a target class, let's say a person. Okay, so given an image, you want to detect whether a person is present or not. So then you can use a binary classifier for that. And again, there are two different variations which you can use to solve this problem. You can only predict a single output. And then single output could be ranged between 0 to 1, or it could be ranged either between -1 to 1 as well. Again, it's like a different variation. It will not matter that much. Let's say you predict between 0 and 1. So at the end of the network's prediction, what you can do is you can put a sigmoid activation function, right? So that sigmoid activation will scale that value between 0 and 1. So now you can ensure that whatever your network is predicting, it will be between 0 and 1. And then you can say that if the prediction is close to 1, you will say that a person is present. And if the value is close to 0, you will say that person is not present. So you can solve that binary classification problem using just single output. And after you have trained your network or your classifier, you can use some kind of threshold. So usually we use like a threshold of 0.5. So if the value is greater than 0.5, then it's a positive sample, mean the person is present. If it's less than 0.5, person is not present. Okay. And this is like a typical architecture for that. And it's just showing a neural network, but a CNN will also have similar kind of architecture. We just predict one value. The other variation is you can use two different outputs. Okay, so in this case, what will happen is one of the output will try to predict whether that object is present or not. So in this case, if we're talking about person or person category, then this will say person is present, and the second output will say person is not present. So you divide it like you share like the prediction from just one neuron to two different neurons. And in this case, what will happen is you will use like the value of this particular neuron to determine whether this particular prediction is active or not. So if this is like close to 1, then you will say person is present. And if it's close to 0, you will just ignore it. And same with this. If it's close to 1, then you will say the person is not present. And if it's close to 0, you will just ignore it. So you're just distributing one prediction to multiple. Now, so that was binary classification. But in real world, what we face is we have multiple classes, right? If I give you an image, then it will rarely happen that you have only one object category in that image. So for that particular problem, what we do is we have a multi-class classification problem, and it's again a simple variation. What you do is you make one prediction for each class, and then that prediction will tell you whether this particular class is present in the image or not. So for each class, you will have one prediction. And again, the values can be between 0 and 1. One says like it's present, 0 will say it's not present. Okay, now if you think about it, if it's just a multi-class classification, and then what will happen is if you're saying that it's not multi-label, which means that in one image only one object category can be present, then if you think about this, given an image, only one of these vectors should be, or one of these predictions should be close to 1, and the others should be close to 0. Because if multiple predictions are active, like close to 1, then that's not the scenario like which you will have in your training data set when you're solving just multi-class classification problem. So to address that, what you can do is you can enforce your network to actually make such predictions, such that all the negative classes will be close to 0 and only the positive class will be close to 1. And we have a special activation function to do that. It's called softmax activation. And some of you might already know this when you were solving programming assignment 1, although it was not a requirement, but I remember like some of you were asking questions about this. So one thing one like important point here is when you were applying a sigmoid activation on these neurons, so you are applying that sigmoid activation independently on these neurons, right? So you just scale the value of this prediction between 0 and 1, irrespective of what value you are getting from this prediction. But in softmax, you don't do that. You scale the values between 0 and 1, but to scale this value, you will also look at what are the prediction values in the other neurons. Okay, so that's a big difference between sigmoid and softmax. So let's like see a concrete example. For example, if you have an image of a cat, okay, and let's say you have 3 different classes in your data set. So you have cat, you have car, you have frog, and let's say this is the positive sample, right? Because this is a cat, but the network is predicting car because this is high. But still, like how you can compute a loss using these values. First of all, these are not probabilities; these are just random numbers, right? So another important aspect of softmax is that it turns like these predictions to probabilities, so that they are ranged between 0 and 1. And also, if you add up those values, it will sum to 1. Okay. So the way to do that is like this simple function. This is called like softmax activation. And what it is doing is you just take this predicted value. You will use the exponential function on that. All right. And in the denominator, again, you have exponent of like all these predictions. You just add up those values. So you're using that as a normalizing factor. So an easy way to do that is you have these values, you compute their exponent. Okay. So this will convert it to this, this will convert it to this, and this will be converted to this. All right, that's step number 1. And then you can add up all these values. So that will be your denominator or the normalizing factor for all the predictions. And then you just divide like each value with that normalizing factor. So that will give you something like this. So if you add up these values, you can see that it's close to 1. And therefore, these are like probabilities. And now you can see that you can easily say it's 87% of chances that a network is saying it's like a car, and 13% chances the network is saying it's a cat. And clearly the network is making a big mistake here, but at least you have a like clear estimate like how much error the network is making. Okay. Now, so that was softmax, and I think you will, whenever you are doing multi-class classification, you will have to use this softmax function. And in PyTorch, I think most of the time, if you compute cross entropy, they have included like this activation in that formulation. So you don't have to do it like explicitly, but you can do this without cross entropy as well, because cross entropy is something else. It's your loss function, and softmax it's not a loss. It's just an activation function, which is scaling your values between 0 and 1 and making them probabilities. Okay. Now let's see, what if we have multiple labels? So right now, I mean, we are using softmax, and we're saying that out of like n predictions, which is like corresponding to n different classes, only one of the predictions should be close to 1, other should be close to 0. But what if you have multiple labels in one image? Which means that you have an image, and in that image you have cat as well as dog. Okay, so in that case, multiple predictions can be active. So in that formulation, you cannot use softmax because it's not appropriate. So what you do is you simply apply a sigmoid, like independently to each prediction, making between 0 and 1, and then train using your normal cross entropy laws. Okay. Sigmoid will just make like each prediction scale between 0 and 1. Okay, so one question from Binay: why cross entropy loss is adding softmax in PyTorch? So I mean they developed the framework, right? And they assume, I mean not assume, but it's fine because in most of the times you are solving you're not solving multi-label. Most of the research is like focused only on like single label classification or multi-class classification. So they have it there. Okay, so I mean I don't have an answer for that, why they did that. Okay, so ideally, I mean, they should have a separate softmax activation, and then they should have a loss function, which should not care about like what kind of activations or what kind of predictions you are getting. So I mean, I think one reason could be like they don't want to burden the user to like write separate activation and separate loss function, and they might be assuming that if the user is not like applying any activations after the final layer, then cross entropy doesn't make any sense. So based on that assumption, I think they put softmax there so that whatever the network is predicting, they will just normalize it and then compute the cross entropy loss. Okay, so that was multi-class, and then we have covered multiple label, and then you all know that then after that we need a loss function which you can use to train your network. So the loss function should like tell you how good the prediction at this point of time is, and based on that it should give you some loss value which is actually used for modifying your network parameters. And we have covered this when we were talking about training your neural network. So this is not anything new. We're just revising this. Okay, so you have a loss function which you use for your network training, and this is like a general formulation of a loss function. All you need is like the network parameters and input data. F is your network, so this will give you the prediction. You compare the network's prediction with your ground truth using some kind of loss formulation. Okay, it could be cross entropy, or it could be something else, maybe mean squared error. And so for classification, we use cross entropy. And again, I think we have covered this, why cross entropy actually works for classification. And so, and simple idea, you can actually try to plot a curve for this cross entropy loss. So if you consider your positive sample for which you should predict like a value close to 1, because that particular class is present, then what will happen is this is your predicted value, right? So log of 1 is 0. So this is actually showing what kind of loss value or the error you will get when you use cross entropy for classification. So when you will predict 1, then the loss is 0, which is perfectly fine. But if you're predicting something like less than 1, let's say 0.8, then you have like a bit of error here. Again, it's not a big deal because 0.8 is like close to 1, because most of the times we use a threshold of 0.5, right? So 0.5 is somewhere here. And in this case, you can see that your the error value is increasing. But if you predict something close to 0, then you can see that it's jumping like to infinity. Okay, so this curve you can easily plot like using this equation. So this is actually just a log plot, in fact. Okay, so and then once you have that loss formulation based on where you are in your loss curve, you can use optimizer. For example, we were talking about stochastic gradient descent, where we take like small steps to move to like the optima. And again, in that will, this is like each step is like updating your network parameters. And this is again like which we have already covered. And so we have like a wide range of optimization algorithms which we can use. So we have already seen what SGD is. We have other variants like Adam, we have error delta. So with error delta, the good thing is you don't have to specify your learning rate. So it will adaptively like automatically find what's the optimal value of a learning rate, and then start training from there. And this is like ongoing research, and people are coming up with like new optimization techniques like every day. So you can also like define your own loss function for finding a loss, that's fine. And once you have everything set up, your network, and you should know like what you are going to predict, and then you should know like if you need any activation function or not. Then you need a loss function, then you have to specify which optimization method you want to use. Then all you need to do is you have to monitor your training loss, or you can also monitor your training accuracy for classification. And this is like a standard curve which you will get when you're training your networks. And I think you have seen all this like in your programming assignment 1. So usually your training loss is pretty low when you compare that to your test or validation loss, and same is with the accuracy. And the reason is because your network was trained on that data, so it can make better predictions. So how close your error curve from your validation is to your network, that tells you like how generalizable your method is. And so yeah, that's all I think we need for classification. With all these details, I think now you know like how to train a classifier, what a classifier is for different problems. Okay, so let me see. Okay, we still have time. One question from Jacques is that sum over classes or batch elements in the cross entropy calculation? Over classes or batch elements? So yeah, that particular sum was over your batch, but you will also have to sum over all classes just to normalize it. Okay, so now we have seen like how we can do classification using classical approaches, where you have to extract like handcrafted features. We saw HOG features, we saw like SIF features, and we know that we can directly use the pixel values if our data is not that huge, and compared that with the CNNs and neural networks. So one big difference is when you are training like a CNN architecture, where you feed in like the actual image, you are learning the features and doing the classification at the same time. And that's the major difference. And what it's doing is it's trying to learn only those features which are relevant to or important for whatever task you're solving, if it's classification or whether it's localization or detection. So for example, if your classification task requires, let's say, background information, then your network will learn that. But if it doesn't require background information, the network will automatically ignore this. And that luxury you don't have when you do handcraft feature extraction, because you don't know what kind of features are useful or not. So you need some kind of domain knowledge to assume that, okay, so these features might be useful, and then you will extract those features. And then you're training your classifier based on those features. And of course, like whatever features you are extracting, all of them might not be useful. And that's why like CNN gives you better performance. Now, what happens is the first initial layers in your CNN, they try to learn like some basic structures. And again, you can see that these are just different edges, like we were determining edges in your HOG feature descriptor, right? So all of these are different edges. Some of these kernels are trying to learn these colors as well. So this was not possible when you're trying to extract handcrafted features, because you would never know like from where to extract color or which color should I extract. For example, in this particular image, it could happen is like this green patch is not relevant for car classification, right? Because car could be present maybe in a grassy field, it could be on roads, or it could be over sand, anywhere. So this is not important. So if you train a network to do car classification, then the network knows that it has to ignore this color, okay? And again, so this is also like a good research area where you try to figure out what exactly your network is learning. And it's still an ongoing research, right? We don't know much about this, but we know that how we can visualize like what kind of patterns the kernels you learned are extracting from the input images. So then what happens is the initial layers try to learn these basic structures. As you go deeper into your network, these structures will be more complicated. Okay, you can see like some shapes here, but some of them are still are like just lines and curves. Okay, and this is happening because in the initial layers, you apply your kernel at a location. Okay, so it's like depending upon what shape your kernel is, it will try to match that shape in the input data, right? So that shape can't be too complicated. But as you move like deeper into your network, then you have combination of those convolution operations, right? You have nonlinear activations in between as well. So then that's why what's happening is at this particular level in a network, you can learn like complex shapes, which are like combination of this, okay? And then as you move deeper, I mean, these complex shapes will be like they could, so this, you can see this is a bird, right? This honeycomb structure. So these are like getting more refined version of the features which you usually found in your input data. So that's like the intuition, and most of the time you won't get like such nice visualizations. It's not that easy to extract these visualizations because these are not just your kernels, right? Your kernel will always be either 3x3, 5x5, 7x7, but you can see that these patches are not 3x3 or 5x5, right? So it's not that easy to directly visualize your kernels. And also remember that your kernels have a shape of, if it's a 3x3 kernel, then it covers like the whole depth. The kernel shape will be 3x3x, let's say 256. Then how will you visualize such a kernel, right? So it's not that straightforward, and you don't have just one kernel, you have lots of kernels. So what you do is you try to reflect back to your input image, and that's called receptive field. So you try to see that if you have like some kind of structure in the receptive field, if that receptive field is activating or deactivating the activation or the output of one particular kernel. So then you say that, okay, then this kernel is trying to predict that kind of shape. So that's like high level intuition, but again, it's a very complicated process. So I just wanted to give you an intuition. So we don't want to go into details of that. So yeah, I think there are some questions. Let me go through those quickly. So a question from Darian: why does the test loss tend to slowly increase over the epochs instead of leveling out? I have noticed this trend in a lot of cases. So when your loss for the test data or validation data start to increase, then it means that you're kind of overfitting on your training data, right? And when you're overfitting, it means that it will not generalize whatever network you are training. It will not generalize well to your testing data. So remember like that curve from, I think it was when we were when we were talking about training neural networks, so we were showing some curves like what is a good fit and what is like an overfit when you try to go through like each of the data point you have, and underfit when, let's say, you have a complex boundary between two classes just to draw a straight line. So that's like underfitting. So when your training loss, or when your testing loss or validation loss is increasing, it means that you're trying to define your boundary like based on each training sample. So you're going through each training sample, and then that's not a good fit, because then you can have a point which is actually from class A, but based on that complicated boundary, it will be classified as class B. So I think I will recommend you to go through those slides. I think it will give you a better idea. I don't have those slides handy, otherwise I would have shown you. But I hope I answered your question. Okay, so Furkan, yes, I think tests should have been stopped at the epoch it started to increase. So yeah, that's right. That's what we do. And that's how we know that we should stop our training whenever your testing and validation loss is increasing, because after that point onwards, it's like just overfitting. So what you can do is you can either stop at that point. The other thing is you can try to reduce your learning rate and start like from that point onwards. So it could happen that your network might still learn something. So you're depending on like how your testing loss follows after that. But that's the strategy you usually use. Okay. So Tushar answered that, and that's right. It starts overfitting on training data. So Mauricio is asking, there will be a meeting next class, or should we just check for midterm assignment on web course? Yeah, so we won't meet during the next class. And I think you should check your web courses at 4:30. So I think it will be released at that time. And then you can work on that and submit it after an hour. So we won't be having this Zoom call next week. And we'll continue continue the next lecture, I think, the following week on Tuesday. Okay, great. So